And it's late getting started. My computer seems to be doing some weird things right now, but let's start from current slide and see if it stabilizes here. Yeah, well, no, it's still flickering. But hopefully it's still doing. I have a bad connection between this and, let's see if I can get it stabilized. It's just going all over the place. Can you see this? It's been running all day fine, but now it's going kind of bonkers. I wonder if it's gotten too hot or something. Okay, let's try to go with it. Last time we did example 3, okay? And let's go back. I wish I knew what was going on with it. Before it was either go out or stay on. Now it's just flashing like crazy. Okay, let's go back. This was our result from example 3, the places where the curve was not smooth, and that were the places at, these along the axis. Okay, otherwise it was smooth. Okay, it's called an epicycloid, by the way. These places where it makes an abrupt change, those are called the nodes, okay, and that's what this is saying. In this figure, the figure I just showed, note that the curve, I meant to ask this first. Any questions before we get started? Okay. Always try to ask that first, because if you have questions, I want to be able to hit them and not get them buried somewhere. Okay. So in that figure, note that the curve is not smooth at the points where the curve makes abrupt changes in direction. Such points are called cusps or nodes, okay? Quite often, I think of node in more of a physical type sense, and I would be more tempted to have highlighted or bolded the cusp part rather than the nodes part, but this is a math book, so they're doing this, and this thing is going nuts, okay? I hope that it holds out and doesn't die on me in the middle of the class. But let's see. Now, bottom of page 830, okay, bottom of 830, it says, most of the differentiation rules in chapter 2 have counterparts for the vector value functions, and several of those listed in the next theorem, okay? And a little bit of a change here, though. There's several different kinds of product rules, so we'll get to that as we get there. So let's do properties of the derivative. These are vector value functions as opposed to scalar value functions. R, bold like it is, and U, bold like it is, are differentiable vector valued functions of some independent variable t, okay? Meaning that the various components are all dependent on t. Let W, now that's not bolded, so that's a differentiable real valued function of t, real valued meaning not vector valued, but number valued. This is a scalar function of t, and C then is actually a scalar, okay? So R and U are vector functions, W is a scalar function, C is a scalar number, okay? So this first is called the constant multiple rule type thing. Derivative of a constant multiple, that's C is a scalar, times a vector function of independent variable t, you can pull the c on the outside of the derivative, and then you have left c times the derivative r prime of t. hopefully just like you would expect. Okay? Next is the sum or difference rule, just as you would expect. The derivative with respect to t, the single valued independent variable there, r of t plus or minus u of t is the derivative of r of t plus or minus the derivative of u of t. In other words, the derivative of the sum or difference is the sum or the difference of the derivatives, just like before. Now, here's the first of our product rules. Okay? Derivative of a scalar function as a function of t times a vector function of this function of t. Derivative of that product is the scalar function times the derivative of the vector function plus the derivative of the scalar function times the vector function. Same as the regular product rule. Doesn't matter whether it's scalar or vector, you do them in that order. Okay? But there's another kind of product you have between two vectors. Two kinds, in fact. One is the dot product. You remember dot products? When you multiply two vectors with dot products, you get a scalar answer. The answer is a scalar number, not a vector. And we'll go back over if we need to see what this is. So the derivative of a dot product of two vector functions is the first vector function dotted with the derivative of the second vector function. Both of these are vector functions, but when you dot them, you're going to get a scalar. Plus the derivative of the first dotted with the second, and that gives you a scalar. So sure enough, it's the same rule, but your answers are all scalars here. Okay? Now, what if you have the cross product? Now, let me back up just a bit. Okay? Here, it doesn't matter which order you do. You could have said this one, this term first and that term second, because that's an addition. Doesn't matter. Addition is commutative. This one, same way. You could have dotted the derivative of this one with the u, and then added to that r times derivative of u. Again, you can just do it. This one, a little bit does matter. Okay? So the derivative of a cross product, which gives you a vector answer, is r of t cross u of t, a derivative of u of t, plus derivative of r of t cross u of t. Okay. Now, whereas it didn't matter the order you do these, and certainly the order you do those, here the cross product order has to be the same. But which one you do first, again, these are just sums, you can add them either way, because vector addition is commutative. But you can't flip these, because flipping a cross product negates the thing. You'll have the opposite answer. Right-hand rule versus left-hand rule, okay? So, I mean, this is still right-hand rule. You see, this vector's going up, that one's going down, so you'll get exactly the opposite answer if you negated any one of those cross products, okay? Now, the next one, this is sort of the composite rule. But notice the composite here. Derivative of a composite of a vector function composed with a scalar function. Vector function of a scalar function is the derivative of the vector function at that same value of the scalar function times chain rule derivative of the scalar function. Okay? Notice they did not have this one on the outside and that on the inside. That hasn't been defined yet, and I'm guessing it doesn't really make sense. Okay? Because you can't take a scalar function of a vector quantity. So that doesn't even make sense. So you have to have the vector on the outside, and then it works perfectly. And then, these are just a couple of other things to keep in mind. If a vector dotted with itself, and you can do that, and when you do it, you're going to get a scalar value. Okay? Of course. Okay? But if you dot a vector function with its derivative, it's always going to be 0. Okay? If this is true, if a vector function when dotted with itself gives you a scalar answer. Now, I said it's always true. One place it isn't. If R of t was a 0 vector. You would get a scalar, but that would be the scalar 0. So that really doesn't make a lot of sense. Because what's the derivative of a 0 of the 0 vector? It's not got a direction, so that doesn't really make sense. So this just means if these are truly differentiable vector value functions, you're going to get a scalar. And because of that, then the dot product of the function and its derivative is 0. Okay. Now, here's the other way to kind of look at that. If here you have a function here, at some point on that function here, it's the vector that represents that. The velocity function, or the derivative function, is always perpendicular to that. Always. Because whatever the curvature here is, the tangent is perpendicular to its radii. So it's not a circle, but if you put a circle there, it would be perpendicular. Okay. So here's example 4, which is, and they do have in the book a little bit of a proof for the fourth property. That, okay, and you can certainly take a look at that, especially if any of you are math majors. Now, if you're pre-engineers, you probably don't care much about proofs. I'm just guessing. Maybe you love proofs. But here's example 4. All right. R of t is equal to 1 over ti minus j plus log tk. U of t, vector function, is t squared I minus 2tj plus k. Find each of these derivatives. Okay? Now, before we start, do any bells or whistles or flags go up when you look at that R of t? One thing t can't be? 0. You can never have 1 over 0. Ever. So t can't be 0. Okay? How about this? No problems here. How about this one? Okay? Not only can t not be 0, it can't be 0 here either, but here t can't be negative. So for this function here, R of t, t has to be positive, not non-negative, positive. They cannot be 0, cannot be negative. This one, no sweat, ski anywhere. Okay? These are good everywhere. Okay? So, just a little observation. I don't know if it'll come into play here. I don't think we're dealing with that, but let's see what we get. So, what's the derivative of the dot product of those two vectors? Now, we could do this either one of two ways. Okay? We can either just take the dot product of them and take the derivative, or we can use the formulas we just had. You have a preference? Let's do the dot product and see what we get. So what is R dotted with U? Let me get my pen up. So R dot U is going to be a scalar function. Anyone know what it is? You multiply the two first variables together, and what do you get? One over t times t squared is t squared over t, which reduces to t, okay, for 2. No, okay. Then the next is going to be a plus, because it's a minus times a minus. So you multiply these two together, and what do you get? Second? Not quite. 2t. Negative 1 times negative 2t would be positive 2t, right? And what do you get when you multiply those two together? Second? Yeah, log of t plus log t. All right, let's combine like terms. 3t plus log t. Okay, now let's take the derivative of that. d by dt of this, 3t plus log t. Ooh, goodness gracious, where did that go? Okay, here we go. What would that be? A little louder? 3 plus what? 1 over t. Perfect. Okay? Now, frankly, I see absolutely no advantage in going back and do it by the formula. Okay? Then you'd have to take the derivative of this, the derivative of that, and then combine the dot products of this times derivative of this plus this times derivative of that. Yeah. You've got a lot to do, and here's your answer. That's pretty simple in my book. Okay? Now, the next one, though, we're going to have to do a little something. Oh, no, we don't do. Wait. Yeah. Okay. Yeah. What would you do first? I'm sorry, I can't hear. Okay, first thing you got to do is find the derivative of u, right? So let's do u prime. U prime of t. And what is that? We haven't done that yet. What's u prime of t? 2t. I, now remember this gives you a vector. 2ti. Next. Minus 2j. Right? Okay. And next. Nothing. No next. Okay. There is a next. It's just the derivative of 1 is 0. Okay. So you got that, and you got to take this and cross it with u of t. Okay? Now remember what I said was probably a fairly easy cross product. You do the I, j, k, and then repeat the I and the j. This is how I like to do it. If you like to do it another way, do it. Knock yourself out. You write the first one that's listed next, and that would be t squared minus 2t, 1, and then repeat the first two, t squared minus 2t. Done. Now cross it with your u prime, which we just wrote, which is 2t minus 2, 0, and repeat the 2t and the minus 2. Okay? Now to do the cross product, we go down the diagonal. And what does that give us? Multiplying. 0. Yeah, because you have a factor of 0. So that gives you 0. Let's do down this diagonal. And what you have? 2t j. Don't forget the j. This gives you a vector. Okay? Then go down that next diagonal, and what you get? Minus 2t squared k. Now you do your up diagonals, but you have to negate them. So this up diagonal, okay, 2 times negative 2 would be a negative 4t squared k, but you negate it, so it's a positive 4t squared k, right? Then go up this diagonal, and what does that give you? 2i. Okay, 2i. No t's involved with that. It's positive because you negated that minus sign. And then when you go up the last one, what do you get? 0. Okay? Combine these together, and you get, so this thing right in here is 2i plus 2tj. I can't write. And combine those two, and you get 2t squared k. Okay? Now, they all have a factor of 2, so I like to go on and take that out. If I take it out, I can take it out of the derivative as well. So let's do a 2 times d by dt of, and what do you have left? I plus 2 plus t j plus t squared k. Okay, let me clean that up just a little bit. Well, I cleaned it up way too much. Okay, now let's take the derivative of that. The 2's out there, and what do you get now? A little louder. 0 for the I. Say again? 0 for J. No, derivative of T is 1. So that's just J. 2T K. Okay? And then if you multiply through with the 2, you get 2J plus 4t k. You don't have to do that, but it just seems like a little easier, right? Okay, so that's our answer there. Now, before I remove things, let me make sure we've done it right. The first one is 3 plus 1 over t. The other is 2j plus 4tk. Perfect. So let's now see how they do it. So our prime of t, okay. I do not know why they have chosen to do the derivatives, but they have. Okay? So you already knew what the functions were, the vector functions were. Now they're going to get the derivatives. You got what those are, not that you needed to. And then it says take the derivative of this thing. Okay? Now, how they're going to do it, lo and behold, is r times u prime plus r prime times u. Really a huge waste of time. Okay, first you had to take the derivatives. Not necessary the way we did it, but here when you did do it, now you have 2 dot products to do. We only did 1. So let's, I wish they had them on the same page so you could see them, but we'll take their word for it. That's, oh yeah, r we remember was 1 over 2. Oh yeah, here, they've written them out for us. This is your r. All right. All right, good deal. Is it Rachel? Yes. Yeah, awesome. All right. Okay. So they've written them out for you. R of t was this. Dotted with u prime they got from up here was that. Then plus the r prime that they got from here is that. Dotted with the u, which they got from the previous thing, which is that. So let's do the dot product here. Here are the i's, so you get 2 here, right? You do a dot product, multiply these two, gives you 2 plus 2, plus or minus 1 minus 1 plus 2. So 2 plus 2, 4. Really high level math here. That gives you 4. There is no Nothing here, so you get a 0. So that gave you 4. You do this dot product, you get a -1, -2. Oh, no, this is a 0 here. So -1. Yeah, because see, there is no j here. This gives you a 1/t. So you get -1 plus 1/t. Okay? And this gave you, what was it, just a 4, wasn't it? Yeah, 4. 4 minus 1 is 3. That doesn't sound at all like the answer we got. So let's see. 2 plus 2 minus 1. Okay. 3 plus 1. Yeah, that's what we got. Yeah. Okay. I think our way was much easier than that one. Okay. 3 plus 1/t. All right. Now, they've already done their derivatives. They've written them. Oh my goodness. Why did they do a second derivative here at all? Oh, because they're using the rule that we had before. No reason for that, but they did it. Okay. So that is true. It's the first cross the derivative of the second, which is that, plus the derivative of this cross that, which is, of course, that. Now, one good bit of information, a cross product of the vector cross itself is always 0. You may not remember that, but that is true. So that term gives you a 0. But still, why don't you just cross these two and take a derivative? Why do you go through all this misery? Stuff. And here they did the same setup that I did. But which one are they doing now? Is that this one? Is the IJK. Yeah, that must be, yeah, that's it. That was the U, and this is the U. Okay, we did take the, yeah, there it is. That. And sure enough, if you do this one, that would be a 0, and imagine this over here. That would be a 0, this over there. No, this isn't 0. That's the 0, and that's why they have the 0 in there. So you still got to do this. Now, without doing the expansion we did, I'll show you the way to do it here. This one's pretty easy because you got a row of 2 zeros from here. Okay, so what you do is take this one times the cross product here. That's a really easy thing to do. First thing you do is determine what the sign of your position is. Here's the position you're starting with, so you do plus minus plus. So you plus minus plus minus plus. Plus minus plus minus plus minus plus minus plus. It always comes out with plus. That is your plus position. So it's 2 times the cross product here, not cross product, your determinant here, which is J. Down diagonals are positive, up diagonals are negative. J plus 2tk. So it's 2 times that, so that would be 2j plus 4tk. And I believe that's exactly what we got as our result. Okay? And boy, are they doing it the long, hard way. Okay. What they're doing is saying, cross out this one and do the I part is this determinant here. Well, that determinant's going to be 0 because you have a row of zeros there. Minus, because this is minus position, plus minus plus, this is minus position, minus the j times the cross product here. Okay, so that's not cross product, determinant here. Plus k, plus minus plus, so this is plus k times this determinant there. Boy, did they ever do this a long way. That gives you a 0. This gives you a minus of -2, so that's going to be 2j, and this will be plus a 0 minus 4tk. So 2j minus 4tk. We've done it about 3 different ways and gotten the same answer. Okay? I think our way was a little bit easier than this way. Though this wasn't bad because your u prime cross u prime has to be 0 and 0 vector. And then the other one came out to be a very easy one to calculate because the u double prime was just 2I. So rather than going through this mess, just use this one comes across here. The determinant there. Keep calling it a cross. You're doing a cross, but it's not a cross product. Okay, 2j plus 4tk. All right, now let's move on to integration of vector value function. Remind me how to take a derivative of vector value function? Take the derivative of each component, go with it, that's it. So, guess how you do integrate vector value functions? You integrate by components, okay? That's all you do. The following definition is a consequence of the definition of the derivative of vector value function of the derivative. We're doing integrals now. So integration of vector value function of RT is f of ti is g of tk. You could put h of tj k if you had that. Where f and g are continuous on some interval a to b, then the indefinite integral, or the antiderivative of r, is okay. I was starting to say I think they're missing something, but I got it. The antiderivative, or the integral of r of t, would then be the integral of f of t dt I plus the integral of g of t dt j. And you're done. Now, what I was thinking was missing, I didn't see a plus c, but they haven't done the integrations yet. When you did this, it gives you some other function, they usually call it capital F of t plus c, and this would be some capital G of t plus c2 or something like that, and then you can combine your c's together. If you had a definite integral over that integral over the interval, a to less than or equal to t is less than or equal to b, then your limits here for the definite integral would be that, and that would be the integral from a to b of f of t d. Evaluate that from a to b, I, plus integrate that, evaluate it between a and b, j, and you've got it. You get a vector. Okay, here you get a vector too. Now, if r of t is a three-dimensional vector in space, f of ti plus g of tj plus h of tk, f, g, and h are all continuous on a to b, then the indefinite integral, antiderivative, is the same as before. The antiderivative, integral, antiderivative, indefinite integral, antiderivative of r of t, the integral, indefinite, antiderivative of f of t, dt I, integral of g of t, dt j. You just integrate each of the scalar functions that are the component functions of your vectors, integrate them, and keep the vector axes, you might say, the ijk. Yeah. And then when you're doing this with definite integral, you just evaluate this between a and b, evaluate g between a and b, evaluate h between a and b, and those would be your real value vector functions. Now, you don't have the t's in there anymore because you evaluated them away. All right, a lot of blah, blah, blah. Oh, more blah, blah, blah. Yeah. The antiderivative of the vector value function is a family of vector value functions. When you're doing just the antiderivative of the indefinite derivative, the vector value function all differing by some constant vector c. So c, no wait, your constants combine to form a new vector, and that's c. Because each one of those would have had a c1, but that's times I, a c2 times j, a c3 times k, okay? So that gives you a vector c, capital C, made up of these three components, object I, j, and k. For instance, if R of t is a three-dimensional vector function, then for the indefinite integral, R of t with no limits on it, not a definite integral, you obtain three constants of integration, one for the f, one for the g, and one for the h. But this is with the I component, that's with the j component, that's with the k component. So your L prime would then be, well, okay, they're saying where this L prime of t gives you that, G prime of t gives you this, H prime, that capital H prime gives you that, okay, your little h. I don't know why they put it in there, but that's true. That's what's true of an antiderivative, okay? Those three scalar constants, which they listed here, those three scalar constants produce one vector constant of integration. Because this C1 is the I component, that C2 is the J component, that C3 is the K component, so you usually just represent as some C, which is, there it is, C1I plus C2J plus C3K is some constant vector C. No variables in that. This is your resultant vector when you did the antiderivative of each of those. And then R prime of t, the R prime of this would give you little f of t, R prime of that would give you little g of t, derivative of this would give you little h of t, and derivative of that gives you 0, because that's a constant vector. There are no t components there, so you get a 0 there. So you wind up right back where you were. Little alpha ti equals little g of tj equals little h of tk. So let's do example 5. Find the indefinite integral. This, what would you get? Can you do it directly, or you need to break it up? Second? Break it up. Okay, let's break it up. Break it up now. Okay. The integral of t dt I, you tell me the next part. Second? The integral of 3 dt j, okay? What would that give you? Second? T squared over 2 plus C1 I plus 3t plus some C2, oops, not squared, C2 sub 2 j okay. Now if you wanted to write that a little bit differently, you could write t squared over 2I plus 3t j plus. Now, here you have a choice. You could say C1 I plus C2 j as a constant vector, or just make it plus some vector c, okay, which is that combination, C1 to I. So that's pretty straightforward, right? Let me erase this and see how they did it. tell you, my screen is strobing way worse than that is. That's coming across fairly constant here. But my screen is just going crazy. Not all of them, but most of my little lights down here are just dimming, brightening, dimming, some of them flashing on and off. I don't know what's going on with it. Okay. So anyway, integrating on component by component, which is what we did, you get t squared over 2I plus 3tj, whoops, plus some constant c, and you got it, okay? They didn't even mess with C1s and C2I's and J's. They just put a vector constant out there, and that's it. So that was example 5. Obviously, the book doesn't, the slideshow doesn't do example 6 or 7. So let's us do 6 and 7. Okay. Evaluate this integral. The integral from 0 to 1 of r of t dt, which is equal to the integral, from 0 to 1. I have had 0 lunch today, so I am running out of energy really fast. The cube root of ti plus 1 over t plus 1j. I'm sorry? Well, it does when I move the screen. It always comes, knock on wood, it always comes back. Okay, sorry about that. It's not going off here. It's just because there's some connector down here. The screen wobbles when I write on it. I try to hold it steady, but any movement, it may disconnect or connect. Okay. J plus e to the minus, I think that's a minus t, my. Cataract is not doing me any favors today. dt. Okay? How would you proceed? You have several choices. Say again? Okay. And break it up as the definite integrals too. So this will be the integral from 0 to 1. Now, while I'm breaking it up, because breaking up is hard to do. No, I'm just kidding. How would you do the cube root of t? I don't like integrating radicals. Yes, right, that is t to the 1/3 power dt, and then make this the component for I. Next, integral from 0 to 1 of 1 over t plus 1 j plus, wait, all right. I left off the dt. Okay. Knew something was missing there. Plus the integral from 0 to 1 of e to the minus t dt k. Now let me pause for a moment here. What's that? You could, but let's, for right now, this is okay the way I wrote it, but I'm beginning to think I would rather see this, the integrand there, be t plus 1 to the minus 1 dt. Same thing, but I just like taking the antiderivative of a power rather than doing of a quotient. Okay? Now, Everything else is doable. So what would that give you? Second? T to the second? 4/3. Okay, over 4/3, which is the same as times 3/4, right? And that's evaluated from 0 to 1. Next. You know, I may go back and do it the other. Yeah, if you add 1 to it, it becomes 0. You can't divide by 0. So let me go back to the other way, because that may be easier to see too. 1 over t plus 1 dt. Natural log, okay? Oh, I forgot my I here. Plus the natural log. Ooh, oh no, this is fine. Of t plus 1 evaluated from 0 to 1 j plus, or maybe not, negative e to the minus t k. And this is evaluated from 0 to 1. Okay? So, this one, no plus c required, because these are definite integrals. So let's do the first one there, and what does that give you? What's that? 3/4. That's all it gives you, right? Because when you put a 1 in there, 1 to the 4/3 power is 1, and 0 is 0, so it's just 3/4 I. You do get a vector, okay? Plus.
Isn't that a 4?
Say that again.
Isn't that a 4 at the bottom?
That's a 4.
Of the integral.
Huh?
Of the integral?
Yeah, 3 over 4. Right. Is that what you mean?
No, like the integral symbol. What are your
Right here.
What are your what are the numbers?
Oh, these are just the limits that you're evaluating that by.
Is it 4? 1 and 4?
No, oh, 0 to 1. No, 0 to 1. Yeah, I'm sorry. Yeah, I always flash my 0. Sorry about that. That's a 4, that's a 0. Okay. Okay, how about the next one? Yeah, I think I heard something. Log of 2. Are you doing minus log of 1? That's what log of 1 is. 0. So that's just log 2j. Okay. Next. This one you have to be a little careful on. Okay, I'm going to put the minus and I'm going to open a parentheses. And what do you get here? E to the minus 1 minus e to the 0. What's e to the 0? 1. Okay? And that's going to be your k. But you can rewrite that ever so slightly as 3/4 I plus log 2j, and then just reverse the order of those and make it plus 1 minus 1 over e times k. What's that? What about it? Right down here. Okay. When you distribute the minus, this becomes minus e to the minus 1, and that becomes a plus 1. So I just rewrote the order of it and did the plus 1 in front, and then minus, each of the minus 1 is 1 over e. So I just did that. And this is Davis, right? This is? Okay. All right. This is really doing strange things now. I'm not doing a thing and it's going backwards. This is bizarre, okay? And it has us in 12.2, which is correct. Oh, it's taking us all the way out. Well, sorry, I've got to get all the way out. Now let's go back in. This is strange. My computer has a mind of its own today, and it's a sick mind, okay? Let's find where we are. That's where we started. Oh, it's not going anywhere. Okay, that was... Oh, we're at the bottom. That must be why it did that. So here's the last slide we did. Or we didn't, I don't know. Go from current slide. Oh, I see. We lost all my annotations because I was writing on this slide. And, whoa, and I lost my pen. I've lost everything. Okay. So the final answer, I had it up there, 3/4 I plus log 2j plus 1 minus 1 over ek. And you don't have to evaluate either one of those. If you wanted to evaluate log 2, it'll be an irrational number. You can approximate it. And 1 minus 1 over e will be another irrational number. You can approximate that. All right, let's do example 7, and let's hope it sort of stays with us on this one. Find the antiderivative of r prime t, which is cosine 2ti minus 2 sine tj plus 1 over 1 plus t squared k. That satisfies the initial condition that r of 0, I can't write, goodness, I can't write, is equal to 3i minus 2j plus k. All right. So it's looking for the antiderivative of that derivative function there. So we're looking for our r of t, which means we're taking an antiderivative of it. So the antiderivative of this would be cosine, the antiderivative of cosine 2t I minus 2 sine t j plus 1 over 1 plus t squared k dt. Goodness. That doesn't seem to be varying very much. But my screen that I'm looking at here is flickering like crazy. And that is driving my eyes nuts. I mean, I can hardly focus on it anymore because it's just constantly going in and out blinking, flashing. I don't know if y'all can see it. May lose everything. I don't know if you can see from where you are. Look at that. That calmed it down. Maybe I should have done that sooner. Now it's doing fine. Nope. Now it started back. It must be a bad connection when it's in this front position like this, but it's not as bad as it was. All right, do what it says. Can you integrate as you go, or do you need to break it up? Huh?
We can do it as we go.
Second?
As we go.
As we go? Okay, what would the first one be? Yep, sine. 2t. Anything else? Over 2. Okay. It's the reverse of the chain rule. Remember? Chain rule would multiply by 2, you divide by 2. I. Okay, let me also do this. I prefer it this way. The book seems not to, but I'd just about as soon do it this way. Let's go on and put a plus C1 in here. I. Because it's an indefinite integral, right? Okay. Minus. Second? 2 what? I don't think so. It's actually a plus 2 antiderivative of sine minus cosine. That's why I made it a plus. Cosine t plus C2 J. Okay. Ooh. Next one's not going to be fun, is it? Did I copy it right? Yuck. You remember what that one is? Substitution isn't going to help you. Second? No, not hardly any way to do that. Now, there's a couple things you could do. No, there isn't. Okay. I was going to say it's not even integration by parts. If you go to the front inside cover of your book, you don't have books, do you? All right. Okay. No one remembers the technique, huh? It's a trig function, not the substitution you make is a trig substitution. You remember that? Second? Yeah. Let t equal tangent u. Okay? Let t equal tangent u. I prefer theta because I think of that. So let t equal tangent theta. Let's do it up here. T equal tangent theta. Okay. Now this is different from the other substitution. The other substitution, you let the u equal some combination of what you got there. This one, no. You let the t be a trig substitution. Just the t. Okay. Now you got a couple of thens. This first implies there's actually a couple things you do. What do you want to do next? Second? Find the a. Is that what you said? What do you mean by a? The what?
Like x squared plus a squared, the formula that equals tangent.
Okay. Well, if I'm hearing you right, the a would be 1. Okay. Is that what you said? Okay. You could do that, but you don't really need it if you're doing the trig substitution. There's a couple of ways you got to go. Okay. Since you're doing the antiderivative of it, okay, well, one thing you can do, if t is equal to tangent t, then t squared, which is what you have here, is equal to what? Tangent squared theta. And 1 plus t squared is equal to 1 plus tangent squared theta. And what's 1 plus tangent squared theta? Secant squared theta. Okay. Now, we're going to be taking an integral of this, so you're going to need to know a dt, because you got a dt in it here. So I guess what I probably should do is write this one out. The integral 1 over 1 plus t squared dt. So we need to know what dt is. dt up here would be what? Derivative of tangent. Okay. Front and side. Oh, you don't have your front and side cover. If you have a book, yeah, you can go and look it up. But in front and side cover, you see derivative of tangent is secant squared. Perfect. Yep, there it is. Secant squared theta dt. d theta is secant squared theta d theta. You always have to have your d with it too. Okay? Now, I think we're ready to do our substitution. Okay? So this integral that we have here, this is going to become the dt is the integral of secant squared theta d theta, that's what dt is, divided by 1 plus t squared is secant squared theta. Okay? Those go out and you're left with a 1. But now we've got thetas, not t's, so this would be, I'm going to write it down here because that's where I've got room, plus, what's the antiderivative of 1 d theta? Isn't it just theta? Okay, so that would be theta, and I'm going to put a C3 here, if I can write, J, K, I'm sorry. Now, we don't have thetas anywhere else in the problem. Let's go back up here to where we defined it, and we see that theta is equal to inverse tangent of t. So what we have here, let me just erase this and put inverse tangent of t, okay, instead of theta, because that's exactly what you got there. Okay. Now, here's why I put the C1, C2, and C3 in there where I did. When R is equal to, R evaluated when T is equal to 0, this would be sine of, okay, if T is 0, 2T would be 0, sine of 0 is 0, 0 divided by 2 is 0, so your C1 is 3. Okay? So here's our final answer. Sine of 2t, yuck. I don't know where my writing is going here. Let me write this a little neater. Sine of 2t over 2 plus 3 I, okay, now, let's see this one. Let's evaluate this one separately. When t is equal to 0, what is cosine? Cosine of 0 is 1. So this will be 2 plus C2 is equal to minus 2. So C2 must be minus 4, right? 2 minus 4 is equal to minus 2, right? Okay, so that's going to be a minus 4, so that'll be plus 2 cosine, I can't write, t minus 4j plus, this is inverse tangent t, okay. All right, let's do the last one here. When t is equal to 0, what's inverse tangent of 0? 0. Because tangent of 0 is 0, inverse tangent of 0 is 0. Okay? So this will just be root 1. So this is, oh, I forgot to write it down. Oh, okay. No, there it is. The 0 plus C3 is equal to 1, so C3 has to be equal to 1. So plus 1K. Okay, let's see how they did. R of t, I forgot to write it down, R of t is equal to 1/2, they wrote it as 1/2, well I wrote it over 2, of sine 2t plus 3 times I plus 2 cosine t minus 4 times j, good for them, plus arctangent t plus 1 of k, perfect, times k. Now they, rather than writing inverse tangent, they write arctangent, which is the same thing. So yeah, that's exactly what they got, and that's how they got it. That's it for 12.2. Okay. Now, by the way, folks, I've noticed, I don't know what's been wrong with my brain, but at the end of the day, when I'm typing in the thing for either my fingers aren't hitting the keys hard enough because I'm so out of energy, or I'm just typing badly or something. So many of the things that are out there on the YouTube videos, it'll be saying chapter 2 point something. It's 12 point something. I think when I type 1, 2 real fast, the 1 doesn't click and the 2 does, or else my keys aren't operating well. I don't know what's going on, okay? But when you see that on the YouTube video, oh, and by the way, my battery, I mean, all that messing I did there, the reason it quit flashing is because the, okay. What I'm going to have to do, and I had to do it last night, I'm going to have to hold my plug in while I do, because my battery was just about to go on me. Okay? So this is going to be a lot of fun, because I'm left-handed and this is not a good way to go. Okay. But anyway, there's our answer. Are you hearing a little beep, beep? Okay, either I'm so close to it I hear it, or I'm going nuts. I don't know. Could be either. All right, 12.2 as opposed to 2.2. That's what I was telling you. Okay. Okay. I'm going to sit and hold this while I do the other. Hopefully it'll recharge my battery. I'm going to need a new computer, I think. Okay, homework exercises 12.2. Do any of the odds 3 through 9. They're all at Calc Chat. 5's at Calc View. Do any of the odds 11 through 17. They're all at Calc Chat. Do either 19 or 21 or both. They're at Calc Chat. Do any of the either 23 or 25, they're both at Calc Chat. 23's at Calc View. Do any of the odds 27 to 33, they're all at Calc Chat. 27's at Calc View. Do 35, it's at both Calc Chat and Calc View. It has 6 parts to it, so it's a little more involved than what it seems like. Okay, do 37 is at Calc Chat. Do any of the odds 39 through 45, they're all at Calc Chat. 41's at Calc View. Do any of the odds 47 to 51, they're all at Calc Chat. 47's at Calc View. Do any of the odds 53 to 57, they're all at Calc Chat. 53's at Calc View. Do 59, well, you can look at 59 if you want. It's exploring concepts. You're certainly welcome to do it if you want. It's a Calc Chat. Should be. There are some proofs, okay? Any of the odds, 61 through 67, if you choose to do them, they're all at Calc Chat if you need some help with them. Then 69 is at Calc Chat, and 71 is at Calc Chat. There's a couple true false, 73 and 75. You can do those if you'd like. They're at Calc Chat. And that's it. Okay. I'm afraid my battery is going to go out on me sometime, but let's try to do as much as we can before it does. All right, so get rid of that and go to 12.3. We've been here a couple times today, haven't we? Okay. Let's start at, goodness, this thing. Okay. Okay, I'm going to see if it's doing this when I turn it around, because that seemed to clear it up some last time. But see, also what it did, it turned off the battery. Do you see it flashing? Okay, that's what I've been looking at all day. When I turned it before, I didn't push in on this, and the battery quit operating. I mean, the power quit operating. Oh, it was running straight on battery, and that's why it stabilized. But then I was running my battery down. You can't win for losing here. Okay, so what I'm going to have to do, actually it seems, no it's not. All right, vector value functions. I may have to sit here and not wave at the board as much. Okay, 12.3 is velocity and acceleration. Okay. Objectives here, describe the velocity and acceleration associated with vector value functions and use vector value function to analyze projectile motion. Have y'all had physics yet? All of you? Yeah, I figure you probably had at this point. Okay, you probably have done this ad nauseum, but let's do it here. Y'all still can't hear the little beeping? Okay, it must be because I'm right in front of it. As an object moves along a curve in a plane, the coordinates x and y of its center of mass are each functions of time. Okay, I don't know why center of mass showed up here, but it did. Rather than using the letters f and g to represent these two functions, it's convenient to write x equal x of t and y is equal y of t. I've been wondering why they haven't done that all along. So the position vector r of t takes the form x of ti plus y of tj. Okay? We could have been doing that all along, but they were doing f's and g, which are fine. No reason not to. To find the velocity and acceleration vectors at a given time t, consider, goodness, this hurts my finger. Oh, yuck, I hit a key wrong. Yeah. To find the velocity and acceleration vectors at a given time t, consider a point Q, which is x of t plus delta t. So it's a little further down the curve, y of t plus delta t, a little bit further down the curve that is approaching a point P, kind of backing up, which is P of x of t, y of t, along a curve C given by this expression. Now I just can't leave this because if I release it, it goes out. This is how I started my class last night. After a while, it stayed in place, so hopefully it'll do the same tonight. I don't know. Along a curve, and here's the curve. The curve is r of t equal x of ti plus y of tj. shown here, okay? Now, I do need to wave my arms a little bit, so I think I'll release this and hopefully it won't blank out too badly. So here's R of t, here's R of t plus delta t. That's the Q point over here. Okay, now what this is doing as the Q gets, okay, and then by definition, R of t plus delta R of t gives you R of t plus delta t. Now, they just named that delta R. That's the difference between this R and that R. Now, as you let Q come back up the curve now, getting closer and closer to P, then this vector, the R of t, this is hard to read, the delta R, which they identified here, and they didn't bold it too well there, is getting closer and closer to 0 as this is moving up this way, up the curve. Okay? So that's what, as delta t approaches 0, delta t gets less and less and less, then the delta R is also approaching 0, so the delta R over delta t approaches the velocity vector, and the velocity vector is that tangent vector there at point P alone. These are the secant vectors, average velocities between here and here, or here and here, or here and here, but this is the instantaneous vector at point P. See what we're going, letting the delta t approach 0. And I better hold this in place. Okay. As delta t approaches 0, the direction of the vector PQ, denoted by delta R, okay, this PQ here is the same as delta R, okay, each one of those, okay, approaches the direction of motion at time t, okay. So delta R is R plus delta t minus R of t, and then when you divide that by delta t, you get that form, and take the limit of that form, and that gives you the, when that limit exists, it is defined as the velocity vector or the tangent vector, both names are right, to the curve at point P. Note that this is the same limit used to define R prime. So the velocity vector is the first derivative of the displacement vector, period. You've had that in physics. So that the direction of R prime gives the direction of motion at time t equals 0. Any time t, sorry. Moreover, the magnitude of that vector R prime is the magnitude of x prime of ti plus y prime of tj, which is the square root of this one squared plus that one squared. And if you think of that, that's the speed. This is a scalar quantity. This is a vector quantity. The speed is a scalar quantity because you're doing the magnitude of it. Okay? I think you all did that in physics too. Okay? Now, similar to how R prime is used to find velocity, you can use R double prime to find acceleration, indicated by these definitions. Taking this out. Okay. If x and y are twice differentiable functions of t, twice differentiable, r is a vector value function given by r of t is equal to x of ti plus y of tj, then the velocity vector and acceleration vector and the speed at time t are given as this. Velocity is the first derivative of r prime of t, which is x prime of ti plus y prime of tj. Acceleration vector is the first derivative of the velocity vector, which is the second derivative of the displacement vector, which is r double prime of t, x double prime of ti plus y double prime of tj. And then the speed, go back to this one and take the magnitude of that r prime, and that's the square root of x prime squared plus y prime squared. Okay? And I'm afraid... All right. For motion along a space curve, add the third dimension. The definitions are similar, so the R of t is x of ti plus y of tj plus z of tk, no h of t here, no z of tk, and then the velocity is the derivative of that, which is right like you see. Acceleration is the second derivative of each of those, and speed now is the square root of the sum of the squares of all three derivative vectors, right? Okay, let's do example 1. Here's your vector r, okay? Find the velocity vector. What would that be? I didn't know I had lost sync, but I have. The velocity vector, v of t, is the same as the first derivative of your displacement vector. And what would that be? You tell me. Say again? Okay, I heard cosine. That's sort of true. Of t over 2. There will be an I out there. There's something missing. Whoa! Everything's missing. Oh, it came back. I do not know what's going on, folks. This is enough to drive me crazy. It operated pretty well all day long. I guess at the end of the day, it doesn't do well. I mean, that happened yesterday too. Okay. This is a minus. Derivative. No, it's not. Sorry, I was integrating. Okay. I'm paying so much attention to this, I'm not. Okay. How about the next one? Second? Negative sign of t over 2j. Okay. So that sure enough is your velocity vector. That's the A part. Okay. The B part, what's the speed? Second? Okay, the square root of, remember speed is the square root of these components. What would that be? Cosine squared t over 2 plus sine squared t over 2. I don't need the parentheses in there, do I? Okay. And that's all, folks, right? But what is that? What is that? Sine squared plus cosine squared is 1, and square root of 1 is 1. So that is, by the way, the velocity vector is therefore a unit vector. Believe it or not, magnitude 1. Okay? Speed of 1. Okay? C. Find the acceleration vector for the particle that moves along the plane C described by that. So what's the acceleration vector? It's the first derivative of the velocity vector, which is the second derivative of the displacement vector. You tell me what that would be. So go back to A and take derivative. What do you get? Okay? Okay. Negative 1/2 sine, chain rule, of t over 2, I. Next. They didn't put parentheses, but it's getting to be so much stuff in there, I think I do like parentheses. What's the next? Okay, but it's a negative again, right? Because the derivative of sine is cosine, but you have a minus sign in front, so it's minus 1/2 cosine of t over 2. I'm going to put it in parentheses j. Okay. All right, they didn't ask for any particular point, so let's see. Oops. Let's see if they get the same thing we did. Okay, let me just check before I displace it. This is example 1. A is, let me get rid of that. Okay. A is V of t is equal to the cosine 1/2 I minus sine 1/2 j. That is 1. This is minus 1/2 sine t over 2 minus 1/2 j. Cosine t over 2. Yes. Okay, so now I can erase it. Anyone need it longer? Okay. So let's see how they... Okay, V of t is the first derivative of R of t, which is cosine t over 2 I minus sine t over 2j, exactly like we did. Then the magnitude of that is your speed, which is the square root of the first component squared plus the second component squared, which happens to be plane 1. Okay, anytime t is a constant. And then the acceleration is r double prime, which is minus 1/2 sine t over 2i minus 1/2 cosine t over, what did I ever say, t over 2j. Okay. Now, I don't know if you're familiar enough with things going on. When you see a constant speed and you've got motion that's going along here, and that constant speed is 1, there's a real good chance that you're moving in circular motion. That's exactly what this is describing. Here the radius of that circle is 2, okay? And you're moving along at a constant along this circle, because you see your I value starts at 0, j value starts up here at 2, and then as the t increases, the I goes around slowly this way, let's see, increasing in I, so it's actually moving in this direction, and but j is decreasing as you go until you get to it moves around in that direction and it completes a total circle. Okay. Now, I'm hoping my battery is charging. I can't tell that it is. All right. They do draw that picture in the book. I guess I should go back to that one. Not going to be pretty anywhere, but we put it here. Okay, as I said, it started up here at 2 because when t is 0, that's sine is 0, so I is 0, and j is 2. Because cosine of 0 is 1 times 2 is 2. But then as t increases, sine is going positive and cosine is decreasing, but still positive, so it's coming down this way. And when you get to pi, when t is pi, then you're down here at pi half, sine is 1, and cosine is 2, and cosine is 0, so you're down there, and then 2 pi would be here, 3 pi here, 4 pi there. That t over 2's, makes it take longer to get there. So there's your circle around. Makes one swipe when t goes from 0 to 4. No, 0 to 4 pi. Okay. That's heavy. The book, not the subject. Okay. All right. Before we get to projectile motion, they've skipped examples 2, 3, and 4. I've been fighting with the computer here. Let me see how we're doing on time. We've still got an hour and 15 minutes to go, right? Okay. I hope the computer holds out. It's flashing like crazy. But let's do example 2. So let's back up and do example 2 right here. Okay, example 2. Sketch the path of an object moving along a plane curve given by r of t is equal to t squared minus 4I plus tj. So let me write that down. R of t, I think we've had this one before, haven't we? One similar to it anyway. T squared minus 4I plus tj. My cataract is really being problematic. Okay? It says first sketch the path of the object moving along that plane curve given that way. So let's sketch our plane curve. Okay? Let's do t 1, 2, 3, 4, 5, 6, 7. Negative 1, 2, 3, 4, 5, 6, 7. Positive 1, 2, 3, 4, 5, 6, 7, 8, 9. Something like that. Negative 1, 2, 3. Okay. All right. What t you want to start with? 0. I like it. Okay. What would be your vector that represent when t is 1? The t is 0. Negative 4i, is that what I heard? Okay. 0j. So that would be the point negative 4, 0, right there. There's our first point, t equals 0. Give me another t. 1. So when t is equal to 1, what's your I value? Negative 3, what's your j value? 1, right? Okay, so there's the other. So guess what, folks? We're moving in this direction. Okay? All right, give me another t. 2. What would be your I value? Second? 0. And what would be your j value? 2. So when I is 0, j is 2. So it's continuing on up the curve like this. Still going in this direction. Very good. Give me another t. 3. What would be your I value? 5i, 3j. So 1, 2, 3, 4, 5i, 3j, something about like that. So yep, it seems to be continuing along like this. And I think the next one's going to be off scale, wouldn't you say? Let's see what it would be. That would be 4 would be 16 minus 4, 12. I don't think I got 12, so yeah, off scale. Continue moving that way. You think that's all there is? We could have a negative 1, couldn't we? So t is negative 1, where are we then? It's still negative 3 on I, but you're minus j, because of negative 1j. So yeah, it's still going in this direction. Yep. Now I bet you the next one's going to be down here at negative 2, and that would be in this direction. And the next one would probably be out here, and that would still be going in this direction, and still coming from there. So I'll just let your imagination fly. So there we've done the first part. Sketch the path of an object moving along. So the path of an object is going to require not just the curve, but also the direction it's moving along the curve. And you really only need probably one arrow. I put several. Okay, one will do. Okay, just to give you an idea. Okay, the next thing it says here, find the velocity and acceleration vectors where t is equal to 0 and t is equal to 2. Okay, here's a hint, folks. Find the velocity and acceleration at any time t, then plug in. Don't plug in first. If you plug in first, you get numbers, take a derivative at 0. Always take the derivative first and then plug in later. Okay, so let's first do velocity at time t is equal to r prime at time t, and that would be equal to what? Yuck. Okay, say again. 2ti. What? I don't know why the I isn't showing up. There it is. Okay, and what? Plus what? J. Okay. Now, let's go on and do our acceleration vector too, since they asked for it. Acceleration vector is your first derivative of your velocity vector, which is the second derivative of your displacement vector. Okay? And what would that be? Two what? 2i. You got to have a vector in there. 2i. Okay? So, this beeping noise and all this mess is driving me crazy. The flashing light driving my head crazy. Okay, so now we go back and plug in when t is equal to 0 and 2. So what is v of 2? What's your velocity at time t equal to? (4i) plus j. You still don't throw that away, so that's 4i plus j. Okay, so at time t equal to, where were we? We were right here, weren't we? So 4i plus j, that would be going up or over 1, 2, 3, 4, up 1. It seems to be right about there. Okay, something like that. Maybe I don't have it far enough up. Let me clean that up just a little bit. Okay. The initial point is here. The terminal point would be, did I say 4? Yeah, 4i. I didn't go over far enough. J. Something about there. So there would be that vector. This is v of 2. Okay? Yep, and they showed that in the book pretty well. What's your a of 2? Why didn't I do 0 first? I don't know. We'll come back and do that. A of 2. What's that? What's the a of 2? It's just 2i. It's 2i everywhere. So your acceleration vector is right there. 2i. Okay? Now. All right. Now, why I didn't do this first, I don't know. What's v at 0? Second? It's just the j, plus j, right? Okay? So that velocity there is v of 0. It's just 1 unit to the north, and that looks about right, doesn't it? Okay? How about the acceleration vector there? That's still 2i. Okay? Which would be right there. Okay. I think we hit them both pretty well. Vi is small and up. Acceleration vector is always 2 units to the right. Get over the 2, it's picked up velocity a great deal. Acceleration is still the same. Now, if you had taken this and flipped it over, that would have been parabolic motion. Gravity would have been down, and it would have been constant, just like the acceleration is constant there. So, yeah, this sort of makes sense. Okay, that was example 2. Now, oh wait. No, wait. Let's do example 3. They make a mention there about an object going around the sun in an elliptical orbit, but a very widely elliptical orbit, follows almost that same pattern. Okay? In fact, that would be a parabolic orbit, but I don't know. I guess if you were swinging off the sun, that would do it, but boy, you get awfully hot. Okay. Let's do example 3. Okay. How are we doing time-wise? Oh, yeah. We go to 5. Okay, we got an hour. Okay. This holding this in place is driving me off. Okay. Example 3, you can see larsoncalculus.com for an interactive version of this type of example. So if some of you don't have books and want to see what this one looks like, larsoncalculus.com, you can go there and see this example 3 or something very simple. Sketch the path of an object moving along a space curve C, this is going to be tough, given by R of t is equal to ti plus t cubed j plus 3tk. Okay, now this one limits the t to be greater than or equal to 0. So you don't have any negative t's in this one. The other one had no limit on the t, so we could put negatives in there. This one says that you're limited to t greater than or equal to 0. Okay? And then it says find, so let's sketch the curve first, and then we're going to find velocity and acceleration vectors at t equal 1 only. So let's sketch the curve first. Now this is three-dimensional, boo hiss. I don't draw three-dimensional very well at all. This is x, y, and z. Okay. Beeping is just driving me nuts. So, give me a few, let me tick off some points. 1, 2, 3, 4. I may not have enough points here. 1, 2, 3, 4, 5, 6, 7. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. Okay, something up there. Give me a value. T. 0. What would be their position then? Zero. You're at the origin, right down there. Give me another t. 1. Where would you be? 1i, 1j, and 3k. Okay, 1i, 1j would be about like that. And then you go up from there, 1, 2, 3. Okay. So it's come out and gone up there. This is a really ugly drawing. Okay, give me another t. 2 is I, that's to here. 8 and j. So that would be about 1, 2, 3, 4, 5, 6, 7, 8. Okay? And then your 6k, right? 1, 2, 3, 4, 5, 6k. So from here, oh, this is going to be so miserable to do. This doesn't look smooth at all. It goes to there. Now, it's all right. It's probably coming around like this. So my first link probably wasn't very good. So let's take that one off of it. It's probably doing something more like that. I hesitate to put anything in here because I'm afraid the next one's going to negate that again. Give me another one. T equal 3. Okay, T equal 3, it's 3I. So that comes up this way, 1, 2, 3. 27J. I think I'm off scale, okay? Really quickly here. All right. Let me see if I can do anything to make this look better for you. They rearranged their axes like crazy. And they don't show but a couple points, so they're no better off than we are. Okay? And they've got theirs oriented slightly differently, but you see we're not far off. We're starting here and then curving around like that. Going out J really rapidly and up K fairly rapidly, then moving out X pretty slowly. Now, what they've done here is just plotted on the XY axes, y is equal to x cubed, which just covers the first two of those. So that would be your curve here, and that would be doing this number here, and would be doing, oh, but you're not going backwards. So that's this curve here, okay? And that's why they show that. I don't know why they did, because that's not the path of the particle, but they did anyway. All right, so we sort of did a draft. Not very good one, okay? I never do three-dimensional well on second dimension. Okay, find the velocity and acceleration vectors when t is equal to 1. Well, of course, you find them first. What is your velocity vector? It's the first derivative of your displacement vector, which would be I 3t squared j plus 3k. All right? Let's go on and do our acceleration vector since we're thinking about it. Yuck. I didn't know my pen was touching the base there. I was waiting for an answer. All right. Your goodness, my eyes are crazy. Is the first derivative of your velocity vector, which is the second derivative of your displacement vector. This is driving my eyes nuts. Okay, what would that be? Six T J, and nothing on I and nothing on K. Okay? Now, they say find these at t equal what? 1. So V when t is equal to 1 would be what? It would be I plus, all right, now this, I don't need parentheses there. I thought it might help, but it doesn't. I can't get them to erase. Plus 3j plus 3k. Okay. So your velocity vector at time t equal 1. T equal 1, I believe, was right about here, wasn't it? Or right here. Right here, I think it was. Yeah. It was right there. And the velocity vector is 1 in the I direction. So it's coming out of the board here. 3 in the J direction. And 3 in the K direction. So it's coming this way and going up, so it's somewhere there. Hard to see on this scale because everything's turned wrong. Let's see if we can do it. I plus 3j, so from this point here, if that's right, I would be here, plus 3j would be 1, 2, 3, something like here, and 3k okay. There would be the vector, something like that. No, yeah. It's so hard to draw this in three-dimensional. What would be your A of 1? (6j). Okay. So the acceleration would be just 6 units this way. All right. That tells me almost nothing, but it is what it is. Okay. So anyway, let's see if the book got them right. V of 1 would be I plus 3j plus 3k, and A of 1 would be 6j. Yes. Got it. All right. Drawing these pictures, trying to draw a three-dimensional graph on a two-dimensional board does nothing for me at all. So let's erase what we've got. Okay. I'm so out of it. Have we had any kind of a break? Do you need one? Or you want to keep on trucking? Anybody? Huh? Do you need a break? No? Or yes? I can't tell what you're saying. Yes or no? Yes? Okay. Should have asked this sooner, but hopefully we can make it for the rest of it. I'm sorry. Should have said this before I turned this volume back on, but I had an adjunct who didn't show up last night who said she was going to, and there was a huge miscommunication. She talked with somebody else who gave her some bad information, and now she says she doesn't think she can teach at all, so now I have a class this far into the term without an instructor. So I was trying to work out something with her on the phone. So anyway, that's why I was gone so long. Sorry about that. I'm the math department chair, so all these problems are mine. And she had said the week before she'd be there. But I told her where, but she had forgotten which campus it was, and the guy who she taught with gave her wrong information because I was in class or somewhere. Okay, probably between classes. Okay. Example 4. Any questions on anything what we've done so far? Sorry this is so broken up today. All right, example 4. An object starts from rest at a point of 1, 2, 0. Now, what does it mean to start at rest? From rest. What does that word from rest mean? Not moving. So get that into something we've been talking about. Second. Okay. It means if it's not moving, the velocity is 0. Okay. So that means its initial velocity, so I'm going to call that v sub 0 is equal to 0. And that's a vector, by the way. Velocity is a vector. So to put that a little more precisely, that would be v at time t0 would be the 0 vector, meaning no 0x, 0y, 0j, okay, at time t equals 0. That's what it means starting from rest, time t equals 0. But it's starting from point 1 to 1, so this would be our r0, okay, the position vector at time t equals 0. So this would be r of 0. So that's where we are at the initial time. An object starts from rest at that point and moves with an acceleration. So now they give us something. Acceleration here as a function of time is equal to j plus 2k. J plus 2k. That's the acceleration, moves with the acceleration of that. Okay? Now, they tell us here, for some reason, the magnitude of the acceleration vector is measured in feet per second per second. I'm going to abbreviate it feet per second squared. That's a little bit easier to write. Okay? Find the location of the object after 2 seconds. So we want r of 2. That's what we're looking for. R of 2. Okay. Where would you go from here? You know initial position, initial velocity, and you know the acceleration vector at all times. You're looking for, let me just give you a hint, position vector first at any time, then we'll calculate what it is at time t equals 2. If you know acceleration, how do you get back to velocity, position? Second? Antiderivative, perfect, which is the same as an integral, right? So what we'll be doing, first let's calculate the v of t, and that would be the integral, I'll first write it this way, of a of t dt, which would be, let's write it this way, the integral of j plus 2k dt. Beeping is driving me nuts, okay? So, what would your v of t be? I'm going to back off to give you a hint here. I don't know if it'll be a very good hint or not, but hopefully it'll be a hint. 0i plus j plus 2k. Is that not the same thing? Yeah. There's just no I, but I wrote one in. So what is your v of t then? Antiderivative of 0. A constant. So let's call that C1I plus okay, it's more than C2. Antiderivative of 1, or dt, would be t plus C2j, right? Agreed? Okay. Next. A little louder. Two T plus C3K. There would be your velocity vector, okay, as a function of time. Yuck. Okay. Now, next issue here, because we know our initial velocity is 0. Because what did they say? From rest. Okay? Meaning it's not moving at the initial position. So if when t is equal to 0, this is 0, guess what C1 is? 0. Guess what C2 is? 0. Guess what C3 is? Second? 3, you said? 0. Okay. Because when t is equal to 0, all those. So all three of those C's are 0. So what we have, the velocity vector is then Tj plus 2Tk, which may have been our first guess if we hadn't messed with that, but that's exactly what it is. Okay? Now let me, yep. Well, yeah, okay. And what do we do from there to get your position vector? That's what we're looking for. Say again? Integrate? I thought that's what you said. Okay. So your position vector, which is your r of t, is equal to the integral of your v of t dt, which would be the integral of this dt. Okay? Now, what's the second? T squared over 2. Oh, wait. Remember my little hint? I should do it again, shouldn't I? Let's do a 0i in there. I'll see if I can fit all these in there. Okay. 0i, where was it? Plus tj plus 2tk. Okay. Now, tell me what is the second? Okay. You want to use C1 again? So it doesn't have to be the same as those, but we'll use it again. C1i t squared over 2 plus C2j plus say a little bit louder. I think it's just t squared. Right? Take a derivative. Yeah, 2t. 2t plus, t squared plus C3k. Okay. Now that accounts for that. So that's our position vector anytime t. We know at t equals 0, we're here. So guess what C1 is? Well, we don't have to write it like this. Let's just write down what R of t is, because I don't have a lot of room. Okay? At time t equals 0, this one is 1. So C1 is 1. So that would be I, if it'll write. There it comes. Okay, and let's get rid of that. Plus, okay, when t is 0. Okay, when t is 0, J is 2. So this will be, C2 will be 2, because T is equal to that disappears. So you have T squared over 2 plus 2 J plus, second? The C3 is 0, but, so that would be T squared, if I could write it, K. The C3 there is 0, okay? That's pretty ugly, okay? So we've got R of T for any T, but we really want to know what R of 2 is. So we go on and plug that in here. So what is R of 2? R of 2 is equal to I, that's yes in Navy, okay, never mind, I'm just kidding, plus, okay, T, yeah, 4 is, T squared, 2 squared is 4, over 2 is 2, plus 2 is 4, 4J plus 4K. Perfect. Way to go. Let's see if that's what they got. R of 2 is I plus 4J plus 4K. Perfect. See how we did it? Make sense? All right. Now, all right, let's look at projectile motion. Okay? You now have the machinery, the tools, to derive the parametric equations for the path of the projectile. Assume that gravity is the only force acting on the projectile after it is launched. Now when it's launched, yeah, say you throw a ball into the air, something like that. As long as it's in your hand, you're exerting a force on it. But the moment it leaves the tip of your finger, you're not acting on it anymore. Now the only force acting on it is gravity pulling down. With the exception of a little bit of air resistance. Right? There's always air resistance. But as long as you don't throw it so awfully hard, it's probably not going to be too much. And the projectile, if it's nice and regular, it may not be too bad. So that's going to be our assumption. Assume that gravity is the only force acting on the projectile after it is launched. As soon as it leaves the barrel of the gun, the string of the arrow, or bow, your hand, whatever it is. So, I thought that was S of 0. So, the motion occurs in a vertical path, plane, okay, which can be, because if I throw it up here, it doesn't go over there or over there. It stays in the plane right here, this vertical plane. And it goes up, and then it comes down. But it stays in the plane, okay? I'm not throwing a curveball, okay? I don't know what that would do. Okay, which represented by the XY coordinate plane. So we're just going to use that to be our vertical plane with Y vertical, X horizontal. Okay? With the origin as a point on the Earth's surface, let's just assume we're throwing it from, no, we're not necessarily throwing it from the Earth's surface, but we could be standing up on top of a building and throwing it, or on top of a mountain and throwing it. And the surface is down here, so we do have some initial displacement, initial height. That would be okay. Now, instant it leaves our finger, the acceleration downward is the acceleration due to gravity. Downward, okay? And it's the same throughout the motion. Wherever that ball is on that path, acceleration is downward. Now, initially, when we throw it, it's at some angle. And if the path is here, that's it. It's the tangent line at that point right there. There's your initial velocity. Okay? And that v sub 0 is called v at time t equals 0. That doesn't mean the velocity is 0. It means the velocity at time t is 0. V sub 0, same as v0. We did that on the last exercise. Now, at some later time, they show the velocity here of t1. That is a, okay, I guess it's okay. I thought that was at the peak, but I guess it is here. There's the velocity there. That's the tangent line there. Here's the tangent line here, Okay? So acceleration is constantly downward. Okay? Your position vector would be that one or that one, you know, but we're not really dealing with that too much. It's the so that's our setup. Okay. For a projectile of mass m, the force due to gravity, I don't know if y'all remember from your physics, hopefully you do, force is mass times acceleration. Okay? The mass m, acceleration is given as a positive quantity, but since it's always pointed downward, that's going to be a minus mg, where g is on the surface of the Earth, 9.8 meters per second, or 32 feet per second, 9.8 meters per second squared, meters per second, or 32 feet per second, okay? In one physics book I teach from, they put 9.80 and 32.2. This is the two digits, that's fine. And it's pointing down, minus j direction. No, nothing on x, nothing on z, all y, okay? And those are the values on the surface of the Earth. By Newton's second law, that same force produces an acceleration, which is acceleration due to time, as a function of time, and satisfies this equation here. Okay? Now, consequently, the acceleration of the projectile is given by ma is equal to m minus mgj, okay, which means a is minus gj. In other words, the acceleration is the acceleration due to gravity. We said it's the only force acting on it, so it has to be the only acceleration acting on it. So this, to me, is somewhat redundant. But this is an acceleration vector pointing downward, magnitude g, where g is either 32 feet per second squared or 9.8 meters per second squared. So here's example 8. No, 5, I can't read. Okay. A projectile of mass m is launched from an initial position r0 with an initial velocity v0. Find its position vector as a function of time. No numbers in the problem at all. Those sub-zeros are all you got, okay? So this is going to be a generic kind of answer. The position vector is a function of time, okay? Where would you begin? And frankly, unless I'm misreading something here, the mass has nothing to do with anything. So why they even gave it to me, gave it to you, well, maybe they're going to ask a follow-up question or something. The mass is not important here if you're dealing with acceleration. But we are on the surface of the Earth, we'll assume that. So what's our acceleration vector? We just gave it minus gj, okay? And since we have the numbers, we don't know which unit they're using, SI, US customary, it doesn't matter. So what we'll do is A is equal to minus gj. Okay? That's where we'll begin. How do we get to a position vector? Very similar to what we just did. Integrate. If you integrate the A, you get v of t. Okay, because A is dv dt. Okay? So this will be integrating. Now I'm going to go on and pull out the minus g. That's just a constant. dt. Okay? And what will that give us? Goodness, this is flashing like crazy. What is the integral of dt? T. Okay? So it's minus gt, okay, plus some vector c. Okay? I'm not going to break it down. Wait. I should break it down. I forgot to put in my j here. Okay? So this is vector J. Plus C. What is that C going to be? Okay? The thing we know is that V at time t equals 0 is V0. So at time t equals 0, the V of 0 is going to be C. So this is our V0. So we can put that in here. So this is minus GT in the J direction plus whatever that V0 is, that vector V0. Okay? Now, guess what we do next? That gives us our velocity vector, but we're looking for a position vector. So what do we do? Second? Integrate again, of course, okay? So when we integrate again, this is the velocity vector, which is the first derivative of the displacement vector. So when we integrate that, we get the displacement vector. Okay? And what will that give us? I'll put the minus G out here, the T in here, dt here, and the J here. And I'm just going to put V0. But we got to integrate that as well. Okay? dt. What do we get? Minus G times T squared over 2, and that's in the J direction, plus, now V0 is just a constant, so let's pull that on the outside here. What's the integral of dt? T. So I'm not even going to write the integral down because I forgot to do it earlier. Okay, so that would be just T plus some constant vector C. Oops. Giving it away. Constant vector C. There. Okay. I should use a different C, but it's the same C. It's okay. Now, but we know with an initial position of R0, that means when T is equal to 0, this is 0, that's 0, so this C is your R0. Right? So, here's our generic equation. R as a function of T, that's what we're looking for, position vector as a function of time, is equal to minus 1/2 GT squared J plus V0, okay, yeah, V0 T plus R0. Remember back in physics? Wasn't that pretty close to what you dealt with? Usually you only dealt with one dimension there. You said 1/2 GT squared plus V0T plus, well, no, yeah, V0T without the vectors on it, plus initial position, R0. That's it. Now, hopefully that's what the book got to. Oh, we can see. But before I do, let's just do minus 1/2 GT squared, got it, plus V0T, they put T0, I don't know, yeah, plus R0. Perfect. All right, let's clear this out of the way. Yeah, they started with A of T is minus minus GJ, which is exactly what it did. Integrate twice. The first time you get some C1, you get minus GTJ plus C1. That's C1, well, okay. And then do it a second time, That's your velocity vector. And then when you integrate that, you get minus 1/2 gt squared j plus c2t plus c1t plus c2. So that's your second constant of integration. And you have used the initial conditions v of 0 is equal to v0, r of 0 is equal to r0 to solve for the constant vector c1 and c2. I wouldn't wait till the end to do it. I'd do it as we came, and that's what we get. Doing that produces c1 is equal to v0, c2 is equal to r0. It makes a little more sense to do it as you're integrating, but they waited till the end. So the position vector is r of t is equal to negative 1/2 gt squared j plus t times the initial velocity vector, whatever that happens to be, plus your r0, which is your initial position vector. Just what we would expect, I hope, from physics. Okay? Now, in many projectile problems, the constant vectors r0 and v0 are not given explicitly. Okay? Often you're given an initial height, which would be your j what am I trying to say? y0j. That's what I was trying to say. I couldn't get it to come out right. The initial speed, okay, and then maybe an angle for that speed. Okay? That is pretty typical. Okay? So, this would be your initial position, and I would call that R0J, okay, positive. And then with this given, your x sub I, y sub j, x would be the magnitude of this times the cosine of this angle, so the speed times the cosine of theta, magnitude of this times the sine will give you your y value. And probably familiar with this too from physics, right? And from trigonometry. Hopefully that makes sense. Because this is your hypotenuse, that's your opposite side, this is your adjacent side. Flip them around however, and that's what you get. Because cosine of theta is adjacent over hypotenuse. X is the component here, magnitude of that is your component there. Y is sine times that. Because the sine of theta is y over hypotenuse. Okay. From the given height, you can deduce that r sub 0 is hj. They call it h, that's fine. Because the speed gives the magnitude of the initial velocity, it follows that v0 is equal to the magnitude of the velocity, initial velocity. So you can write, it seems redundant to put these in here. If this is v0, why put this? Okay, so v0 cosine theta I plus v0 sine theta j. That's your initial velocity. Okay. So the position vector can be written of this form. R of t is equal to negative 1/2 gt squared j. We had that from before. Plus t v0, we got that last time, and r0, that's the thing we came up with in our last problem. But we've just been given this. We still have this, negative 1/2 gt squared j. That stays the same. But now this initial velocity vector is v0 cosine I, so this t is times that, plus t times v0 sine jt, sine theta t, plus h, that's your initial height. So this is your next most generic form, where you know your initial velocity, initial speed, and the angle which you did. The rest of it, and your initial height. So, losing my voice, sorry about this. Breaking this down, let's put the only I term out here, v0 cosine theta times ti. Why they changed the order, I'm not sure, but it is. These are constants. There's your variable. There's your vector. Okay? And then combine all these j's together from right to left, kind of h plus v0 sine theta t minus 1/2 gt squared. All this times your j. And sure enough, you got it. Now, can't think of any reason they did this except getting the pluses in front. Okay? Otherwise, I would have written it the other way, minus 1/2 gt squared, and then the t term, and then the constant term. Okay. So here's the position vector for a projectile. Neglecting air resistance, the path of a projectile launched from an initial height h with initial speed v0, nothing about velocity except speed, which is its magnitude, and the angle of elevation theta from here is described by the vector function that we just came up with. R of t is v naught, v0, the speed, times the cosine of that angle, times ti. That's the only thing in that direction, and that's the only thing ever in your horizontal velocity direction. That's your only horizontal velocity. It doesn't change. Okay? Cool. Well, no, it does. As time increases, that shows it's increasing. I'm having a little bit of problem with that. Okay, well, we'll go on from there. Something is not quite ringing true there, but I guess it's okay. All right. Okay, plus, and then your vertical, you have initial position, and then your initial vertical component, and then your acceleration down. Okay. Oh yeah, I'm sorry. Yeah, this makes perfect sense. Its position is increasing as you go to here, but its speed is constant. Okay, that's what that makes sense. So yeah, the position is increasing this way at a constant speed. The vertically, you start at an initial height, and then you have an initial component, but then it's being dragged down by the acceleration. So that's changing. Where g is the acceleration due to gravity. Yeah, that's okay. That's correct. So let's do example 6. Do we have time? No, we don't, do we? All right. Sorry about that. Talked too long. Hopefully I'll have all the mess straightened up with my scheduling next time. We will pick up in example 6 next time. We came that close to finishing. We hopefully will finish it next time. Homework exercises include any of the odds 3 through 9. They're all at Calc Chat. 3's at Calc View. Any of the odds 11 through 19. They're all at Calc Chat. 15's at Calc View. Any of the odds 21 to 25. They're all at Calc Chat. 21's at Calc View. 27 through, goodness gracious, 39, I believe it is. Wow, okay. They're all at Calc Chat. None of those are at Calc View. 41 should be at Calc Chat. 43 should be at Calc Chat. 45 should be at Calc Chat. Wait. Not get further than we did. Because we didn't do the example in projectile motion, let's stop at 39. Okay? And then we will pick up with projectile motion with 41. All right, good deal. Any questions? All right, good deal. We'll start with example 6 next time. Okay?